Nevada looks empty, but that emptiness hides a failure so precise, so microscopic, it quietly broke an entire agricultural system. For decades, farmers here did everything right. More water, better fertilizer, smarter machinery. And still, the harvest kept collapsing. Not because the land was dead, not because the sun was too harsh, but because one flower refused to open. And when engineers finally understood why, the solution sounded completely insane. Releasing millions of bees into the desert, no hives, no honey, no protection, just salt, soil, and a species nature had erased from memory. If you enjoy massive engineering projects, hidden biological systems, and technologies that reshape the future, make sure to subscribe, like the video, and comment where you think this approach could work next. Because this wasn't luck. It was designed, and it nearly failed at every step. Nevada isn't just dry, it's chemically hostile. The soil here is loaded with ancient lake minerals, alkaline compounds that harden into a crust when exposed to heat. To farmers, it looks like dirt. To plants, it's armor. Water doesn't move normally through it. Nutrients bind to the wrong molecules. Roots struggle to breathe. Over decades, yields declined not in dramatic crashes, but in slow erosion. A few percent less each year. Quiet enough to ignore, deadly enough to matter. What made it worse was the irony. The more farmers tried to fix the land, fertilizers, conditioners, soil treatments, the more unstable the ecosystem became. Methods that worked across the Midwest failed instantly here, and yet one crop refused to disappear: alfalfa. It survived where others surrendered. Its roots reached deep into mineral-heavy ground. It tolerated heat, it stabilized the soil. On paper, alfalfa should have saved Nevada agriculture, but something invisible was holding it back, and that invisible problem lived inside the flower itself. Alfalfa flowers don't open politely. Each bloom is a mechanical device, a tiny spring-loaded system called a tripping mechanism. Inside the petals is a sealed chamber holding pollen. To release it, a pollinator must land with the correct weight, at the correct angle, applying the correct force. When that happens, the flower snaps open violently, slamming pollen into the insect's body. It's efficient, it's precise, and it's brutal. Most insects hate it. Honeybees, the backbone of modern agriculture, learned quickly. After being struck repeatedly, they began stealing nectar from the side of the flower, avoiding the mechanism entirely. The flowers bloomed, they looked healthy, they fooled everyone. But they weren't producing seeds. Fields of purple stretched across Nevada like a promise and delivered almost nothing. What looked like an irrigation problem was actually a biomechanical failure, and it got worse. At first, farmers assumed they just needed more bees, so they imported them by the millions. But honeybees are learners. Over time, entire colonies adapted their behavior. They remembered which flowers hit back. Each season, fewer flowers were tripped. Pollination rates dropped further. In some areas, adding more bees actually reduced seed output because the bees crowded out other insects that might have tried. The system entered a feedback loop: more flowers, more bees, fewer seeds. By the early 2020s, production costs exploded. Seed yields became unpredictable, and Nevada's alfalfa industry stood on the edge of collapse. That's when someone looked backward instead of forward, not to new technology, not to genetic modification, but to a dusty line of forgotten research. And what it described sounded impossible. Decades earlier, long before industrial farming reshaped the West, Nevada had a native pollinator unlike any other: the alkali bee. It didn't live in hives, it didn't make honey, it didn't migrate. It lived underground, carving precise tunnels through alkaline soil that other species avoided. Its size, its weight, its landing behavior all matched alfalfa's flower mechanism almost perfectly. When it landed, the flower snapped. The pollen is released, the system worked. But the alkali bee had one fatal vulnerability. It required salty, compacted soil at very specific moisture levels. When humans began fixing Nevada's land, reducing salinity, flattening fields, applying chemicals, the bee lost its home. Its tunnels collapsed, its larvae drowned or dried out, its population vanished quietly. By the time agriculture noticed something was wrong, the bee was already gone, or so everyone thought. And that raised a terrifying question: if the missing piece wasn't technology, but a living system, could humans rebuild it? The proposal sounded like sabotage. Instead of reducing soil salinity, make it worse. Instead of smoothing fields, roughen them. Instead of modernizing, reverse engineer the past. Researchers proposed building artificial alkali beds, salt-crusted soil layers, underground irrigation tuned to millimeter precision, moisture gradients engineered to stay stable for weeks. The margin for error was microscopic. Too dry, and larvae would die. Too wet, and the tunnels would collapse. Too much salt, and nothing would survive. And then came the most controversial step, releasing millions of bees. No hives, no shelters, no guarantees. Critics argued it was reckless. Some warned of ecosystem disruption. Others said the bees wouldn't survive a week. If this sounds unbelievable so far, hit like, because this is where the gamble truly began. On paper, releasing the bees was only half the risk. The real danger lived underground, mundi sur in variables no model could fully control. The alkali bee doesn't tolerate mistakes. Its tunnels must maintain a precise curvature. Too shallow, and surface heat cooks the larvae. Too deep, and oxygen levels drop just enough to slow development or stop it entirely. Engineers discovered something unsettling early on. The soil didn't behave like a uniform material. It behaved like layered memory. Decades of farming had created invisible strata, compacted zones, collapsed root channels, mineral seams left behind by irrigation cycles. If a tunnel intersected the wrong layer, it could collapse days later without warning. Moisture added another layer of risk. The underground irrigation system had to deliver water in pulses, not a flow. A steady trickle would soften tunnel walls. A sudden surge could flood brood chambers within minutes. Some engineers quietly raised concerns that a single valve failure could wipe out an entire generation of bees before anyone noticed. Then came the temperature. The salt crust acted like insulation, but also like a heat trap. During extreme heat waves, surface temperatures spiked far beyond forecasts. If the thermal gradient shifted too quickly, larvae could fail to develop properly, weakening the population long before adults ever emerged. Predators were another unknown. The salt discouraged most insects, but not all of them. Certain parasitic species are known to sense underground larvae chemically. If they adapted, they could invade the tunnels undetected, destroying brood chambers without leaving surface evidence. And then there was the worst-case scenario no one wanted to say out loud. Behavioral rejection. Some experts warned that reintroduced bees might refuse to nest at all. If they dispersed instead of digging, they would vanish into the desert, leaving behind nothing but empty salt beds and public humiliation. At that point, the project wouldn't just fail. It would confirm every criticism that ecosystems can't simply be rebuilt, that lost relationships stay lost. If this level of risk surprised you, hit like, because the most dangerous part was still invisible. For weeks, no one knew whether the experiment was succeeding or quietly collapsing beneath their feet. The first signs didn't come from spreadsheets, they came from silence. Normally, alfalfa fields buzz unevenly, bursts of activity followed by long gaps. This time, the sound never dropped. Researchers noticed something else that didn't fit their expectations. The bees weren't clustering, they were spreading. Instead of concentrating near the salt beds, alkali bees fanned out across the landscape in expanding arcs, some traveling farther than historical records suggested was even possible for the species. That raised immediate concern. Longer foraging distances meant higher energy demands. If the bees burned more energy than the fields could support, the population could collapse after a single season. Then came the flowers. High-speed field cameras revealed what the naked eye couldn't. The bees weren't just triggering the tripping mechanism, they were doing it faster than any pollinator previously measured. Some experts caution that excessive tripping could damage flowers before fertilization is completed. Too much force, too often, could shorten bloom lifespan. For days, the data looked contradictory. Pollination rates surged, but seed formation lagged. That gap sparked anxiety. Critics argued the system might be front-loaded. Spectacular early activity followed by delayed failure. A biological boom with a built-in crash. Then, quietly, the numbers shifted. Seed pods began forming in clusters instead of isolation. Flowers once dismissed as spent reactivated. Even late-season blooms began setting seed, something rarely seen in Nevada's climate. Soil sensors picked up another unexpected signal. Root systems beneath the alfalfa fields grew denser and deeper than predicted. Some agronomists believe increased seed development altered hormonal signals in the plant itself, reinforcing root growth and stress tolerance. That discovery raised a new question. If pollination efficiency could reshape plant physiology, then the impact of the bees went far beyond seeds. If this reversal caught you off guard, comment below. Would you trust a system this dependent on a single species? Because by the time harvest arrived, the debate wasn't over success, it was about consequences. At first glance, Nevada's rebound looked like a clean victory. Seed yields surged, fields stabilized, costs dropped in ways spreadsheets rarely show all at once. But beneath the celebration, new questions began surfacing. Questions far more uncomfortable than the original failure. The entire system now depended on a single biological relationship. One species, one soil profile, one narrow range of conditions. Some experts warned that this wasn't resilience, it was precision balancing, a system that works brilliantly until it doesn't. Climate variability became the next concern. Alkali bees evolved for specific temperature rhythms and seasonal timing. If heat waves arrive earlier or winters shorten unpredictably, emergent cycles could drift out of sync with alfalfa flowering. That mismatch wouldn't cause a dramatic collapse. It would quietly reduce efficiency year by year. The same way the original failure began, there was also the question of scale. Rebuilding alkali beds isn't cheap. Salt sourcing, underground irrigation, and land preparation. All of it requires capital, expertise, and time. Large farms might manage it. Smaller producers likely couldn't. That raised an uncomfortable possibility. A future where only heavily engineered farms can sustain seed production, while others fall behind, locked out by cost rather than climate. Ecologists raised another concern. By recreating a hyper-specialized environment, humans were effectively freezing one version of an ecosystem in place. Adaptation slows when conditions are controlled too tightly. If a new pest adapts to the salt beds, if a pathogen targets alkali larvae, there is no backup species waiting in the wings. And then there's the precedent. Nevada proved that lost systems can be rebuilt, but only with deep historical knowledge and extreme precision. That sets expectations dangerously high. What happens when policymakers assume every ecological collapse can be reversed with enough funding? What happens when a restoration attempt fails? Not because it was wrong, but because it was incomplete. The bees didn't just restore agriculture, they exposed how fragile modern systems really are. And that realization may be more important in tosses and more dangerous than the harvest itself. The alkali bees didn't save Nevada by accident. They exposed a truth that will define the next decade. The future of engineering isn't just bigger machines or smarter software. It's understanding systems so complex that removing one tiny part can collapse everything. If this approach spreads, agriculture could shift from force to precision, from domination to restoration. But if it fails, if ecosystems prove too fragile to rebuild, the cost won't just be crops. It will be food security itself. So the real question isn't whether Nevada succeeded. It's whether we'll recognize the next invisible failure before it's gone forever. If you want more deep dives into the technologies and systems shaping our future, subscribe, like the video, and let us know your thoughts in the comments, because the smallest solutions often decide the biggest outcomes.